Ну хорошо, давайте тогда начинать. Значит, сегодня у нас вторая лекция последней части курса, и я передаю слово Мауро.
Хорошо, спасибо. Last time we checked the just the definitions here of 1 second. Yes, okay. We build just a Markov chain and a Markov process on a finite space. Yes, so G is a finite set. We think it's a graph. Similar construction is needed. Is possible, of course, for much more general Markov processes. But the ideas that I want to present are the same. And like the strategy of the proof is the same. So it's not like we need just more formalism, okay? But the main ideas are the same. So that's why I try to keep this framework simple. Then, according to our interest, we can eventually do it on different spaces. And remember, what we are given, for instance, in the discrete time case is a probability. Pxy is the probability of jumping from point x to point y. And in the continuous case, we are also given some rates, c of x of which point x. I don't remember if we call it c of x or cx. Which is like a parameter associated to how much time on average I wait when I reach point x, how much time I stay in point x. Like in discrete time, this time is always 1, and in continuous time it's random. And if we want the process to be Markov, it's necessarily exponential. So one over c of x is the mean of this exponent is the average time I stay in point x when I pass in x. But this is okay. We are not going to use this today. And so just to recall you, and also another data that we needed to build this process was the initial distribution. Where we started, we can start in a deterministic point, but more in general, we can start with the probability measure in G, yes, with probability mu x, we start in point x. And then, okay, we introduce the functional, which is which is in reality rather elementary, but also very kind of used functional, not just for Markov processes, right? Which is called the entropy, relative entropy. And it's defined as follows. So we have a measurable space E, and we have a reference M. So here the role of, and we have two probability measures. Okay, they could be measures, not probability, but say probability measures, mu and M. So the role of these two measures is different. This entropy is not symmetric, okay? M is like the reference measure. You think that you are given a space equipped with a measure. Sometimes maybe equipped with the distance and the measure, but like we are given this structure. And so h of mu given M is the sort of the cost, the information of mu with respect to M. The excess of information of mu with respect to M. Yeah, so h of mu M is not equal to hm mu. It's a completely different, okay? H mu M is the entropy of mu when the reference is M. So this was defined as the Supremum we checked last time of measurable bounded functions phi. And okay, when I write measure of a function, this means integral of phi and the mu. And here the space E is not necessarily, or not at all, finite, yes? For us, the space E will be like a probability measure on G, measures on G, or this kind of stuff. E will not be G. So even if G is finite, these notions of relative entropies and other functional we will give on general spaces. Okay? So if M and mu now are probability measure on this space E, that can be anything, we defined in this way with the Supremum the relative entropy, and we have briefly checked that this is plus infinity. It's quite obvious. If mu is not absolutely continuous with respect to M, it doesn't have a density with respect to M, and otherwise it's the integral in the mu of the logarithm of the density. So the mu in the M, I hope everybody is familiar with the Radon-Nikodym derivatives. So the mu in the M is a function on E, and we have checked that this integral is well posed because you can write it in the M as the integral the mu in the M log the mu in the M in the mu. So since x log x is bounded from below as a function, This integral is well defined. We checked this last time. And okay, so maybe what I didn't, I just last time a bit threw to you this function, and maybe I just, okay, then we will check again what we were saying last time. But before doing this, maybe I want to make a little remark how we can interpret this relative entropy. Of course, this originally, this kind of things were introduced in very classical statistical physics, like Boltzmann, like logarithm of the number of the states, this kind of thing. So how we can motivate it? Let's us take a finite space, n points. I should have called E probably this point, not omega, sorry. So let's suppose that E has finitely many points. And what is like the value of the information? I give you the information that some event in E happened. What is the value of this information? Of course, I mean, it's not mathematical. Like, how can I define the value of some information? I give you this information, okay? You play on horses in a hippodrome and somebody tells you this horse will win. What is the value of this information? If the horse was the strongest one, it's not very good information. If it had high probability of winning, this information is not worth a lot. If it had very small probability of winning, it's worth a lot. So what is the value of an information? So first, this is just means, what does it mean information? Okay, it's not like mathematics. So let's think that it's I of A, the value of the information that K happened. Let's think that it's a function of the probability of A. The smaller is the probability of A, the bigger is the value of the information. Well, this is the first property, and then it has kind of a natural property, because if I first tell you that A happened, and then I tell you a completely different information, independent, that B happened, I tell you the horse will win, and tomorrow I don't know, the price of the oil will be this one. Okay, these two informations, they are like independent, probably, and the information of the two kinds of, the value of the two informations is like the sum of their values. It's not, so I'm thinking that if two events are independent, the information that the intersection happened is the sum of the informations. So this plus the fact, since they're independent, the probability of the intersection is the product of the probabilities. So you see that if you think that the information depends, is a function of the probability of an event, this immediately tells you that the information is just the logarithm of the probability of the event. Okay? So it's just an informal argument. It's not like, it's reasonable to think that like the information of an event, the value of the information is proportional to the logarithm of the probability that this event happens. It's just like motivation, it's not mathematics. Up to some constant, okay, this constant is, we take it equal to 1. Indeed, we will take, in some sense, we will be interested in limits, and we will take limits where this constant sort of goes to 0, and how this thing scale when this constant goes to 0. So when these events becomes less and less likely, yes, small probabilities and thus small constant to have finite limits. Okay. So that's the idea. So now this is the logarithm of the event, the information of the event. The value of the information that an event happened is like proportional to the logarithm of its probability with a minus. So if we sample on 1 to n, we start to extract numbers on 1 to n, each with probability 1 over n. So each element with the same probability. So every time we get an information of value log n, I tell you, 3, 7, 8, and so on. Each time is log n, the value of this information, because each of them has probability 1 over n minus 1 log 1 over n log n. Good. But suppose that instead of choosing them with probability log n, with probability 1 over n, we choose them with we choose I with probability pi. So p1 is the probability of choosing 1, p2 the probability of choosing 2, and so on. So in this case, the average, how much on average, every time I extract, how much kind of information I give you on average, well, it will be minus, because events I will happen with probability pi. I will tell you I with probability pi. So it's just the average of log pi, which is minus sum over I pi log pi. Okay. So the difference of the value of the information if I extract them in the most random way, 1 over n, 1 over n, 1 over n, or if I extract with probability measure pi log pi, is log n minus the sum of pi log pi. So this is, I can rewrite it as sum over I pi log pi divided by 1 over n, because the sum of the pi is 1. So I can put this sum of pi, I can take log n within the sum of the pi, okay? And okay, this is a trivial equality. And then you see, I can write it exactly. This is what? This is the, if I think that mu is the probability measure on my space that gives 2i probability pi to the point I, this is the integral in the mu is just a sum of the log of the radon-nicotine density of the mu in the m. Yes, if we have, if a space is finite, or if mu and m and mu give a finite positive probability to a point, the radon-nicotine derivative, the mu in the m in that point is just the ratio of the two probabilities. So this sum in this case, so in general is this integral when it's finite. Okay, in our example, when m is uniform and mu is a generic measure on a finite space, just this gives like the difference of average information between that you get if you sample events with m or if you sample events with mu. That's like on a finite space, that's the idea. And then so here, this is the idea where omega is finite and the reference measure is uniform, okay? How do we generalize this idea of excess of information, excess of value of information, or default of value of information? If we do it on a general space with general measures, and the idea is with this relative entropy. So that's what it gives. It's just a generalization of, I don't know, value of information to when like the reference thing is m, what like typically rightly should happen is sampling with m is your reference measure. Instead, you use mu, I don't know to say, pay an information price, which is this relative entropy. It's just the interpretation. I don't pretend any mathematical meaning, just okay, if you accept that value of information should have this property, you can get this interpretation. Okay? Is there any question on this? I'm just repeating with some comments what we did last time. Just this relative entropy, I sort of threw it to you, so I just want maybe many I'd already seen. I don't know if exactly this argument, which is quite silly, but I don't know, similar statement. Okay, so I just, last time I left you with an example, but we didn't have time to do it in detail. I will give a very quick sketch of the proof because we will prove more interesting result, but just to give a taste, I wanted in the first lecture to give a taste of the idea, and okay, let's finish it now, and at least some ideas coming from this, like the strategy we will use later. So, okay, now we have a Markov chain, okay? I start in x0 with probability px0, x1, I go to x1. So if I go to x1, I continue like this, okay? That's what was an example of our framework, but sorry, last time we left in the case where in reality, pxy was my. I always jump, independently of where I am, I always jump always with the same measure, my. I go to y with probability my, okay? Independently of where I am. So this means that if I also start with the same probability m, this sequence x0, x1, x2, and so on is a independent, identically distributed sequence. All the xi are independent because every time it doesn't depend to where I jump, and all the xi have the same distributions m. Is this clear what this means? Yes, I think it's clear, yes, for everybody. So we want to prove in reality a theorem that we could prove in 1 million different ways. Again, it's just an example of the technique, not the result. So now we take this object, which is called the empirical measure, that you have probably already met in doing ergodic averages. You just you have a sequence. In some sense, this is not random so far. Okay, if you give me a sequence with values in G, which we are thinking like a trajectory is in G, we just consider a measure that gives to a set the Pn depends on n. So you consider this trajectory up to time n after n steps, and Pn is just 1 over n, the sum of the delta over xi. So you put mass 1 over n every time in the point where this path passes. Okay, every time, if you are considering Pn, every time it leaves a little rock of weight 1 over n in the point where it passes, and at time n there will be a weight distribution on the sides of this graph G, of this finite set G, on the points of this finite set G, and that is our probability measure, is the distribution of these weights. So it's the probability measure that gives to a set the Pn of a set is the fraction of time that your path spent in that set. Okay? If half of the time you were in point x7, in point, say, A, point A will have probability one half of the time. Okay, then just beware. So the law, now this, if you give me x, if you give me a trajectory, I make this probability measure. If the trajectory is random, like in this case, Pn will be random. Okay, the law, the distribution of Pn will be a probability measure on this kind of object. So it will be a probability measure on the space of probability measure on G. Beware, probability measures on G. So beware that, like, this first P is like the randomness, and the second P of G, that's not like, of course it's probability, but it's not like randomness in some sense. It's just the object we are looking at. Here it would be completely equivalent if I consider, instead of, I don't know, 1 over n, 5 over n, okay? If I define the pi n 5 over n, it would have been completely equivalent description, this rock weighted 5 times the previous one. So this big Pn would still be a probability, the law of pi n, but not on probabilities on G's, but of measure of weight 5 on G, measure of total variation 5 on G. Okay, so the randomness is the first P, and the P of G is our object. P of G is our space we call E. Okay, the space where we considered the entropies before would be P of G. Okay, not G, P of G. Okay, and then we had this, in reality, almost trivial statement. Oh, the proof, okay. So fix a probability measure on G, which is anything, okay? First point A, 1/3, point B, 1/10, and so on, any probability measure. And then take a kind of a possible law of Pn, not the one of this Markov, of this IID sequence, any law of of Pn, okay? So any probability measure on probability measures on G. And suppose that that Qn converges all these measures. So Qn, P of G is a space. Think of that P of G is some space. Actually, G is finite, so P of G is a simplex. If G has n points, P of G is a simplex and dimensional. Okay, so I don't know. It's like a triangle P of G. So Qn is a probability measure on this triangle, and it when n goes to infinity, concentrates, all this measure concentrates in one point. Okay? So this convergence on a finite space is not really, okay, what does it mean? It means that, for instance, that, okay, in what sense converges, maybe we can, it means that integral of continuous function converge, I will tell you in a second, but I think on a triangle is quite clear. We probably measure on a triangle, you know what it means, converge, we converge on probabilities. Then the limit of the entropy of Qn with respect to Pn, Pn is the original one, the true law of pi n, the true law of the empirical measure. So the cost of the information, if I want to produce mu, not what pi n would produce by itself, which is just m by ergodic theorem, but another measure, mu, okay? How much I have to pay must diverge with n, and must diverge at least as, okay, so if I divide by 1 over n, it must be in the limit at least the relative entropy of mu with respect to m. Okay? So, like, you sample an IID sequence all with the same probability measure M, okay? So the empirical measure will converge to M. Like, I don't know, for instance, you start to throw dice. Each one of them, probability, each result probability 1/6, okay? If you track the empirical measure, in the limit, you will see that each result will happen 1/6 of the time. I want to cheat. I want to throw dice randomly in such a way that in the limit, I don't convert, like how many times I see 1, how many times I see 2, how many times I see 3, and so on. It's not 1/6, 1/6, 1/6, and 1/6 of the total in the limit when the number of throws was to infinity, but is mu1, mu2, mu3, mu4, mu5, and mu6 for some mu that I decide. So not the original one. What is, how much information on average I have to give up, okay, here. If I want to converge in the limit to mu, no matter how I decide my strategy, how I change randomly these dice and so on, I will pay at least, okay, here this function is again a relative entropy, but here could be some, here should be some function of mu, and this is again a relative entropy, okay, this is due to the fact that we took IID sequence of mu over m. So beware, this is a relative entropy on the probability measures on G, this is a relative entropy on G. So, okay, probability measure on probability measure on G, this is a relative entropy on probability measure on G. So in the left-hand side, according to the previous definition, we would have E equal to P of G, and in the right-hand side, E would be G, okay? So in the example of the dice, okay, this object here, H of mu given M is uniform measure, mu is whatever I decide, and the H of mu given M is exactly just this sum, okay? So on the right-hand side is an expression with finitely a sum of 6 terms. Probability with which I want to get 1 times log of 1 divided by 1/6, probability of 2 log of probability of 2 over 1/6, and so on, which we checked it's possible. Okay, that's the first statement, this inequality. The second inequality is there is a way, okay, to, sorry, here, I didn't fix it from last time. There is a sequence Qn that converges to the delta over mu is the same things, such that the limit of the entropy, so this Qn, there is this Qn that converges to mu, the same as here, to the delta over mu, such that in the limit, I pay exactly the relative entropy. Actually, in this example, okay, I can do it for every n without limit. Okay, so this tells me that the cost of producing a different results of the dice, not m, not 1/6, 1/6, 1/6, 1/6, but mu, in terms of information, is this sum. P1, if I want to produce P1, P2, P3, and so on, is so if in the limit I want to see a fraction P1 of times 1, a fraction P2 of times 2, and so on, is the way to do it is the minimal cost I can pay is this sum pi log pi over 1/6. Okay. So if you want to prove it in this way, the proof in reality is elementary, but not so immediate to some extent. I mean, it's immediate, but we need to just spend some time writing down the things. So, but it's, in its spirit is completely trivial. What is not trivial is the statement. As P of G, if you never see too much, I don't know, probability. So, so first, Qn and Pn, they are probability measures on G. But, okay, let's first, yes, sorry. Let us start from this, which is simpler formally, because I just need to show you a Qn, okay? I need just to show you a Qn. You give me mu, I need to give you a sequence of laws on P of G, such that the relative entropy of Qn with respect to the one of the law of the empirical measure is bounded, in the limit is bounded by this. Okay, this is trivial how to do it. Okay, you give me mu, and I take Qn.
Sorry, please. What's the difference between 3 and 4? Well, I see that there are different signs of the inequalities, but what's the difference between formulations?
Yes. So, okay, thanks. So 3 is no matter how I converge to delta of a mu,
Okay.
I pay at least this function of mu.
Okay.
And second is, there is a way, so the first is for each way I converge, at least this. And the second is, there is a way that pay at least this, so at the end it means equal.
Okay, so this means that in fact we can construct a sequence µn such that will be exactly the same. Okay.
Yes, yes, yes. But beware, in general, the inequality will be strict. Just there is one way, or maybe many ways, okay, but like typically it will be strict inequality. Then there is a way, maybe actually many, but there are ways to make it equal. But if you just, I don't know, to say, throw these dice and not like more or less independent, still in this case you have to throw, for instance, these dice still almost independently, or independently, or say almost independently in the limit. Otherwise the inequality will be strict. So again, two statements. No matter how you converge, you pay at least this amount. There is a way of convergence that pays at most this amount. Then, of course, if you put together 3 and 4, the one that makes at most this amount, it actually makes an equality.
Okay, thank you.
So let's start to find the sequence in the second statement, because it's very simple. I want to produce mu. I take the empirical measure where each, so Qn is the law of pi n, is the law of the empirical measure, but when I extract x1, x2, xn, not with probability m, but with probability mu. So again, if the problem is you are throwing dice, each result is probability 1/6, and you make an IID sequence, 1, 2, 3, 4, 5, 6, each element of the sequence random with the same probability 1/6 for each entry, I want to produce mu. I take Qn to be the law. If instead of doing 1/6, 1/6, 1/6, I drove with P1, P2, P6 that I want to get, okay? The law of large numbers tells us that Pn converges almost surely to Qn, so that in particular Qn converges to the delta of a mu, because for every function f, 1/n, the sum of f of xi, if this is an IID sequence, every, okay, say bounded measurable f, we are on a finite space, this will go, so for any f, because we are on a finite space, this will go to mu of f, the integral f in the mu, the average of f with respect to the law of the xi. That's the law of large numbers. So here the space is finite, so f of xi is bounded. There's no any integrability issue, and or continuity. And so if I take Pn to be the law of pi n when the xi are distributed according to mu, if you want, this means they push forward through to pi n of the product measure on G to the n with marginal mu. Okay. Then what I get is, so certainly Qn converges to the delta of a mu, law of large numbers. I need to check the relative entropy and check that when I divide by n, in the limit is as most h of mu given m. Okay, and actually I don't even need to take a limit. This is an equality for every n, because the relative entropy of Qn given pi n, this is, so this is not bigger than the relative entropy of the product measure done all with the entries mu. So this is the law of x1, x2, xn when I sample each xi with mu, with respect to the law of x1, the original law of x1, x2, n, when I sum all of them with them. Why it is smaller? Because the empirical measure is a function of x1, x2, xn, is 1/n, the sum of delta. So if you check the definition here with the supremum, yes? So on the left-hand side, I had, if you want, a supremum of functions of the empirical measures. And on the right-hand side, I had supremum of the functions of the same object, but a function of x1, x2, x3, and so up to xn, okay? So of course, the right-hand side is bigger because it's a supremum of the largest class of functions. If you want how much information is in the empirical measure, is if you know the empirical measure, you know who are x1, x2, xn up to the order, yes? Because you just see the weights. You know that you pass it in 1, you pass it in 2, you pass it in point A, in point B, in point C, but you don't know which one was the first, which one was the second. So So on the left-hand side, you just start taking the supremum of a function that are symmetric in x1, x2, xn, and on the right-hand side, you take the supremum on every function of x1, x2, xn. So that's why there is an inequality. And now, okay, the empirical, you just write down explicitly with the logarithm the expression for the empirical measure. This is, so the random-Nicotian derivative of two products is just the product of the random-Nicotian derivatives. Therefore, you get that the log of the sum is the sum of the, sorry, the log of the product is the sum of the logs. But here, every time you just, I don't know, when you integrate xi, you get log of d mu xi over dm xi, and then you integrate in d mu, but all the mu x with xj different from I, they integrate to 1, because each term, once you make the sum, each term in this integral only depends on xi. So you get a sum always of the same thing, which is h of mu given mu. Okay? Actually, here I wrote inequality because you could even check that it is an inequality, even this one. But okay, I think it's so. Is it clear? Is it, questions on this? If you have doubts on random-Nicotian derivatives, which on a finite space, this just means the ratio of the probability of a point, tell me, because we can review it, okay? So we get n times the random. Okay, and then so this is just the proof of the second statement. Okay? There exists a law Qn that converges to delta of mu such that the relative entropy is bounded by this. This sequence is just the law when you take independent with a different probability. The first statement basically is so the other inequality is basically the same. We need to just to say that if you don't take them independent, you pay more information than if you take them independent, because the reference was product. So that's the idea. So suppose I have a Qn and I have that converges to the delta of mu, and I have to prove that the relative entropy is bigger and the limit is bigger than the relative entropy of mu with respect to n. Well, if Qn is not absolutely continuous with respect to Pn, this relative entropy will be infinite. So in this case, I have no inequality. I have to prove that this relative entropy is bigger than. So if it's not, if this is infinite, okay, I just go along a subsequence where it's finite. Otherwise, the inequality is trivial. So if it's absolutely continuous, this must come also. This must be a push forward to the empirical measure. Okay, Qn must be the law of 1 over n sum of delta of xi, where the xi have some distribution. Let's call lambda n this distribution. So lambda n is a probability measure on g to the n. It's a probability measure of x0, x1, x2 up to xn minus 1. So the relative entropy in this case, yeah, that's the first point. The second point is that lambda n is invariant by permutation. So it's a probability of x1, x2, xn, but how much, I can assume it. Okay, if you don't want to assume this, you can make here not an inequality, an inequality with a bigger or equal. But since how much information is in the empirical measure is the same information that is was in equality to xn up to permutations, so you can assume that already the original law of the x1, x2, xn was invariant by permutation, because you will always get the same Qn. I try to say it better. You take a probability measure on x1, x2, xn, and then make the empirical measure pi n. I take a diff, okay, and I take the symmetrized version of your probability measure. So I make 1 over n factorial, the sum, I make the convex combination of all of your probability, of all the possible, of the law of all the possible permutations of x1, x2, xn with your probability measure, convex combination, since there are n factorial terms, each of them divided by n factorial. And the relative n, so we get the same law of the empirical measure, right? Because the empirical measure doesn't see this, is invariant under permutations of who is x1, who is x2, who is x3, who is 1, 2, 3. So, so that's why when you do the empirical measure of Qn given pi n, you get, so exact, so if Qn is the push forward of a probability measure on G to the n through pi n to the minus 2 through pi n to the empirical measure, the relative entropy of Qn through pi n, just by its definition, you can check easily, that is the relative entropy of lambda n given, okay, the law of the product measure with marginal m, provided that lambda n is invariant by permutation. If it's not, you get the symmetry. If lambda n was not invariant by permutation, you get the symmetrizer of lambda n, because pi n only depends on the symmetrized version. If this is not completely clear, it's not a real problem, because this is just to get a few ideas on how we formally prove these other things later. Okay, so it's if you have, if the formalism is elementary, it's okay, but if it's instead unclear, do not panic, okay, because in any case, we will derive a stronger statement than this. Is just to get an idea. So, okay, so this is just another say, the cost, the information I have to give you, if I give you the cost of the information that I give, if I give you the empirical measure, is the cost of choosing x1, x2, xn, but not with the original product measure law, with a different one. Okay. So now we just need to check, okay, now lambda n is invariant by permutation. This means in particular that every marginal, the law of x1 under lambda n, the law of x2 under lambda n, the law of x3 under lambda n, they're all the same. And let's call mu n, so it's probability of G, the law of any on xi under lambda n. Then we want to prove that h of lambda n given the product measure is bigger or equal that n given the relative entropy of the marginal mu n of lambda n with respect to n, with n times, okay? So if lambda n would be product, this would be equal and would be just the same computation as before. And I want to say, if it's not product, it's bigger. Okay? Because here on the right-hand side, there is a product. For n equal 1, this is trivial, otherwise proceed by induction. Though, since this is just to get an idea, avoid too much formalism, let's write for big N equal 2. Then we should do it for any n. I should write x1, x2, xn. It's too much notation. So lambda n now is a measure on 2, not on x1 and x2. And the relative entropy is this object on the left-hand side. Integral in the lambda, log the lambda in the, here is product measure and 1 x2. Now, you know that I can, okay, this proof just works on any space. Space here is fine, but I can disintegrate a measure lambda, the lambda n x1, x2. I can write it as the mu x1 is marginal over the first times a measure on x2 that depends on x1. So lambda n x2 x1, lambda 1. So the measure lambda 1 of x2, if you want, is the law of x2 conditional to x1. In probability, one usually writes this kind of name, but in analysis, one usually writes a disintegration in this way. So on a finite space, this measure here for fixed x1 is just the original measure lambda n of x1, x2 divided by lambda of x1. So here I'm just writing, divided mu of x1. So here I'm just writing lambda, sorry, this, lambda of x1, x2 as mu of x1 times lambda of x1, x2 divided by mu of x1. So I just multiplied and divided each term by mu. But now what I notice that, again, this is the log of a product of radon. So the log of this product is the sum of the logs. So the first log here, when I integrate, you see, it's log of d mu x1, dm of x1, doesn't depend on x2. So this x2 integrates away the integral of, so when I integrate away x2, I get the first marginal in the integrand of lambda n, which was mu n. So the first part, the first kusok, is just h of mu n given m, yes. And the second, what I get you see, I write it, this integral in x1, x2, first integrate it in x1 and then in x2. And so if I do the same disintegration here, I get the integral in the mu of x1. And what remains is just the relative entropy with respect to, is an integral in x2 with x1 fixed. So in x1 fixed, what I get is exactly the relative entropy of lambda x1 with respect to m. Yes, because here the integral in x2 is exactly integral in the lambda x1 of log the lambda x1 in the m. And now, okay, that's just a way of saying that if you don't take it product, you pay more in this trivial example of ID random variable, because now H is the same. But you see that by A, we proved last time, is just supremum of linear functions, that the relative entropy is convex. It's a convex function, for instance, of the first, it's actually jointly convex, but it's a convex function of mu, of the first entry. So the average mu n is a probability. So the average of over x1 of this family of probability measure is bigger than the relative entropy of the average by convexity. Yes, if I have a convex function in some convex space, convex space like probability measure, the average of the function is smaller than the function on the average, but the function, since again lambda was invariant by permutation, when I average lambda 1 over with respect to the first marginal, I get the second marginal, which is again mu n by invariance by permutation. So h of mu n given m plus h of mu n given m. This is exactly h of mu n given m. So I get twice h of mu n given m. So the only inequality, I use it here. This would be like equality if it's product, because this doesn't depend on x1 if it's product. Lambda n x1 is already mu n if it's product. It's not product, and I get, but if it's not product, I get an inequality. It's just a way of saying that if you don't throw these dice in, you want to cheat, but you do not throw the dice IID, you have to give up more information about the fact that you are cheating than if you were throwing them IID. Okay? So the relative entropy of Qn given Pn, no matter who is Qn, you take mu n to be the marginal of x of one of the xi, and it will be bigger than n times h of mu n given m. Then h of Qn Pn will be bigger or equal than n h of mu n given m. Now, remember, we divide by n. Okay, so we get, and we are trying to prove the first inequality. So we divide by n, we get that before taking the limit is already bigger of h of mu n given m. Then we take the lim-inf, but look, this is not hard to check it. If you want that the empirical measure converges to the delta of a mu, at least the marginal of each xi has to converge to mu. So this mu n is convergent to mu. Mu n is convergent to mu. Did I write this? Yes. Mu n is convergent to mu, because otherwise you cannot converge to the delta of a mu. It's a necessary condition that the marginal one converged. So once it's exchangeable. So H, we proved also last time, is a supremum of continuous functions. So it's lower semi-continuous. And as such, if mu n converges to mu, h of mu n given m in the limit is bigger or equal than h of mu given m. So we proved this. Okay, that was just an example. Like now, so this, I like this interpretation. How much kind of information you have to pay if you want to cheat? Okay, you have a problem. Stochastic dynamics, maybe somehow a deterministic dynamics with random initial data, like a dynamical system, or this kind of things. So typically, something will happen. Yes, here the lower large number or ergodic theorem will tell you that pi n converges to m. You sample each xi with m. Now I want to cheat. I wanted to make it converge not to m. I want to make it converge to another object mu. How much information, what value of information should I give up? Okay, this information will go to infinity, in this case like n, because otherwise if it doesn't, if you don't let the information go to infinity, you will converge to the same n. There is no way of doing so. It will go to infinity, okay? And but you can find exactly the sort of the minimal cost of cheating, okay? These things is, I always, when I speak about this, I say this, that this is used a lot of this kind of techniques inside trading on the market, okay? You know some information about some stocks. I don't know, you know that tomorrow Apple will report earnings and they are higher or low, let's say are higher than people expected. So you have some information, this information has some value. You want to make money on using this. It's illegal, it's absolutely illegal. If you have this, you can only trade if you have the same information than the others. It's called insider trading. How should you make money legally? Since it's illegal, you want to use this, you want to make money, you want to perceive your strategy, for instance, converging to, I don't know, making $1 extra million, trying to give up as little information that you knew more as possible. You have to give up some information because when trading, you show that you have more trust than others in, I don't know, they will declare a higher, their share report will be positive, okay? But there are many ways to make this, to trade, making this extra $1 million using this information. And you exactly will try to do it, minimizing the relative entropy of like your model with extra information with respect to the original model with respect to less information. There's a lot of literature on this. Usually the literature on scientific journals is written like you are the police and how to find out who is cheating. But in reality, a lot of people, I think, they just really try to cheat because it's it's a big problem in the stock market, I think, who is cheating, who is doing insider trading. Okay, this is so it's a bit of the same idea, just we did it just for dice, cubic in this example, but it's really pretty much the same. Yeah, okay. So if this argument here, just for your problem, is not so clear, yes, trying to rewrite, it's not strictly needed for us, but it's just to manipulate, I don't know, random negative derivatives and integrals and so on. Try using the fact that G is finite, so random negative derivative in a point is just the ratio probability. Try to rewrite this proof, it's not clear, okay? Because I didn't give really all the details. Okay, now I want to, okay, that was end of this first motivation slot, and let's start to do some more precise mathematics. So we exactly, first I want to, so I want in a completely general framework where we have just a space and so on, to tell what does it mean to give this kind of convergence as the one we have seen for IID random variable, for empirical measure IID random variables, and then to do something for like currents, similarly for Markov processes. Okay. So just first, what does it mean, this kind of inequalities you have to give up at least? Okay, this is one interpretation. I want to give you a second interpretation of the same object, quite precise, with fluctuations, with the likelihood of events, okay, with how improbable is that something happens. So I take a space E. Again, E will be like for us probability measured on G. E will be like currents on G, this kind of things. And we think that E is equipped with a nice topology and a nice sigma algebra. What I mean nice, I mean that as a topological space, it's nice. Okay, for instance, it's separable, it's metrizable, maybe this matrix can be taken complete, and the sigma algebra is the Borel sigma algebra. Okay, so there is a bit of relation between the topology and these probability measures, okay, because the sigma algebra is the Borel one. And for the sake of simplicity, I take this space to be compact. Okay, all these things can be made more general. For instance, what you really need is you don't need that E is compact. You just need that compact subset have this kind of property. You can be on a general E, but its compact subsets should have this kind of properties, and the Borel sigma algebra should also be the one generated by the compact set, not only by, so the sigma algebra generated by compact coincide with sigma algebra generated by open. Little things that like we are working on things like probability measure in a nice space will have this kind of problem. All the space we have will certainly be in this class. But just I want to keep compact keys because if you start to do non-local compact, a little bit of technicalities arise, but the ideas are exactly, and the statements are exactly the same. So I don't want to spend time on pathological topological spaces, which are not particular interest. So the space of probability measure on this space E, we can equip it itself with a topology, which is the weakest topology, such that the map that associate to F mu of F, so the integral in D is continuous for every continuous F. So that's exactly the problem. If A is not compact, because if it's locally compact, okay, you can still take here a reasonable algebra of continuous functions. But if it's not locally compact, you have to take this topology, the weakest topology, such as this map is continuous for all functions that are uniformly continuous with respect to an equivalent completely bounded metric on E. Okay, there is a way to do it in general. Okay, so in this topology, that's exactly a bit tricky because something is saying the topology, something is saying the convergence. But if it's compact, it's not a big deal. So in this topology, a sequence of probability measure on E converge if and only if to a limit mu, if and only if the integral of all continuous functions converge. Okay. So the fact that here is continuous is the link with the topology of being close. So if you put this topology on E, P of E is itself a compact space, it's itself completely metrizable, it's itself separable, so it itself comes with a nice topology. So, like, for instance, E is a, I don't know, R, okay, no, finite, 0, 1, and these are probability measured on 0, 1, but they are still a pretty nice space when equipped with this topology. There are many different distances that you can, for instance, define on this space, like Levi distance or Wasserstein distances, and they all metrize the same topology. Okay, so the convergence, since it's compact, is always the same. And another example, so probably the fastest way to write this, an equivalent distance, so one that generates topology, is this, and the distance between the probability measure is the sum of a k. So I take fk. So here I made a small mistake. This is not fj. The second one is also fk. So this is a k, the second index also. So you take so E is compact and separable. So C of E is also separable. You take a dense subspace of continuous function on C of E, countable dense set of continuous functions. And, and you just say the distance between 2 and mu is the sum of k of 2 to the minus k, the minimum between 1, okay, this function are to be, or I could have just taken all the functions less than 1 or less than half. And okay, mu of fk, and then the difference of the integrals. Okay. So it is clear that if fn converges to f, mu of fn converges to mu of f for every f, this distance between mu and mu goes to 0. But the opposite is also true, because if this distance goes to 0, this means that all, if you check with a bit of detail, all the mu n of fk must go to mu of fk for every k. But since they are a dense, uniformly dense subset of C of E, you will have it for all functions. So, okay. Just to say that this space is also nice, but convergence in this space, you converge in this space, means that average of all functions converge. Okay? If you think that mu n, that you have a sequence of random variables xn, and mu n with values in E, so random variable with values in this topological space, and you think that mu is the law of random variable x, then mu n converges to mu in this topology just means that xn converges to x in law. Okay, so you actually already met in this compact case this topology. So okay, and then I define, and then also you give me a sequence an that goes to infinity. Okay, so you give me two things now: a sequence of probability measures and the sequence of real numbers, μn and an. For us in the example before, Mn was the law of the empirical measure by n, and an was just n. And I defined these two functions. So maybe I could have written this, or maybe not. I think I wrote it somewhere. This object I, what it is a function from E, from the space to 0 infinity. As an object, this I is these two i's, I bar and down bar, up bar. So I down bar, what it is? Let's read it together. In point x, it's the same thing as before. In point x, I bar x is the infimum. So I take the infimum over all the sequences of probability measure μn that converge to the delta over a point x. So I have this space E. I fix a point. I want to calculate I down bar in a point x. I take all the probability measure that concentrate the sequences μn that concentrates in x when n goes to infinity. All the measure concentrated in this point x. So μn converges to the delta x in this topology, of course. And then I consider the liminf of 1 over an, h of μn given mn. So for each n, I consider I fix then how much information I need to give for μn with respect to mn. This I can expect that, for instance, if mn converges somewhere and I want to converge somewhere else, this will has to go to infinity, this relative entropy. And I divide by an. Okay, this number. So this an should be like how fast. I mean, this an, in some sense, this definition makes sense for any n and for any mn, but like relevant one will be like how fast this information has to explode. But I do liminf, and when I do I bar up, it's exactly the same definition. So still I minimize the cost. Yes, it's a minimization problem. I always try to converge to the delta of x as cheap as possible, paying as little as possible in terms of information. But now I take the lean soup. So the difference is, I don't know how to say, is only in this limit, okay? If for n even, mn is in some way, and then odd, mn is different, these two will be very different. But it's not like one is a soup and one is an inf. In both cases, I'm interested in minimizing, okay? Just one is a liminf in n because the limit may not exist, and one is the lean soup in n, okay? So in very often they will be the same, you can hope. I of x, when I rescale with a of n the cost divided by n, is the minimal cost of conversion to x. But since this limit of minimal cost may not exist, I bar down is the liminf of this cost, and I bar up is the lim sup of this cost. So of course, I bar sup is bigger than I bar down, and moreover, they are lower semi-continuous. Lower semi-continuous means that sub-level sets are closed, or if you want, it means that the limit, whenever xn, so these are now our functions on, not on P of E, functions on E, not on probabilities, on E, on E. The limit, when xn goes to x, the liminf of xn is, of I of xn is bigger or equal than I of x. So, for instance, if it's continuous, it's lower semi-continuous, but if in a point is smaller than the limit of the other points, then it's not continuous, but it's lower semi-continuous. This is bigger, is not lower semi-continuous. Okay? Why is this? Very often, in minimization frameworks, in variational frameworks, lower semi-continuity is like a natural hypothesis because so functions that are lower semi-continuous admit a minimum on the compact. Functions that are upper semi-continuous admit a maximum on the compact, and as you know, continuous admits minimum and maximum over compact. So these are easily seen to be lower semi-continuous because if xn now converges to x, you can just take a double sequence. First you converge to xn, and then slowly you converge. So say xm converges to x, okay? First, you take a sequence when you minimize that converge to xm. So you do a double indexed sequence. So you make a diagonal argument, if you understand what I mean. And it's very easy to prove that these two functions are lower semi-continuous. Okay, that's like I don't know how to say why I can choose how to converge to X. So if I do it through a subsequence, so if I do it through, I don't know how to say, this limit cannot be smaller than I of X, because otherwise I would find a better sequence that converges to X and that makes I bar in the limit point smaller. So it's obvious that it's lower semi-continuous. Both of them are lower semi-continuous. And next, okay, sorry, I don't see, let me check the time. I want to give you an important proposition. So I up bar, this one up, I don't see, okay, I bar is the largest lower semi-continuous function. Lower semi-continuous means that it has this property, the sub-level set are closed, so now our space just moves. Is the largest lower semi-continuous functions from E to 0 infinity, such that okay, let's read this inequality. The lim sup of -1 over n log of n of a is bigger or equal for each measurable set A, this is bigger or equal than the infimum of the closure of A of I of x. So consider all the functions that have this property. The largest lower semi-continuous one is I up bar. That's what claimed the proposition. And the second statement is that, okay, the reverse inequality, but here you put the interior of A with the other inequality, and this is I up down, okay? Now, what do these two inequalities, this is an important proposition that we prove, but first let's check what it means before giving a proof. So, suppose, otherwise so I can write more or less equal, so otherwise I should write inequality. Suppose that these two functions are the same. If they are the same, one says that a weak large deviation hold. This is just a definition, weak large deviations. Then you see, in this sense that you have one inequality on the interior and one on the exterior, on the closure, this, if you like, change the sign, take the exponential and so on and so forth. So in this logarithmic sense, this means that the measure of a set A behaves as e to the minus an infimum over A of I of x. So in reality, you have two inequalities, but like if the infimum over the interior of, so if the infimum is not attained at the boundary of A, okay, the two inequalities coincide. So when n goes to infinity in this logarithmic, so this means that if you take the logarithm on both sides, you divide by n and take the limit coincide. Okay, that's what it means, this writing. More or less equal, this, okay, in this sense. But this means that, you see, if you want, do you want to know the probability of a set A when n is large? If I bar and I bar coincide, the probability of the set A is e to the minus an infimum of the x in A in I of x. So, for instance, think that this set, think that Mn converges to a point, and that this set A contains this point, or contains neighborhood of this point. Then Mn of A will converge to 1. So this means that I of this point will be 0, because otherwise here you will have something that goes to 0. n, remember, is positive, so the infimum of I of x over this set must be 0, no matter what the set that contains the limit point. So I of this point must be 0. But if this set doesn't contain point, so mu n, now Mn is converging to a point, and this set A doesn't contain this point. This tells you that exponentially with rate 10, the probability will be small. Now, this could be surprising because you tell me, okay, why is exponential? I can pretty much think of a probability that doesn't concentrate exponentially. I don't know. Gaussian measured with variance log of 1 over n. This is not exponential in n, the concentration. But in this case, is an will be log of 1 over yes, okay, minus will be log n. An will be log n. So I don't know to say. There is an universality here. I'm claiming that any sequence of probability measure, any an, I have a PDF, so any an, you will have this kind of formulas, okay? Actually, along such sequence, we will see. How is it possible? Well, is it possible because in some sense, if you choose the wrong an, okay, we'll see in a second, you will get still a trivial statement. But in any case, you can, okay, let's check it later. So this can be surprising that you have this expression, but you see I'm using nothing. Any sequence of probability measure have this property, any sequence. So in reality, this always happens. So so I of x, so an tells you at what speed this measure, I don't know, vanishes away from sets, okay? Like in the limit, the sets will, the probability will go away from the sets. At what rate? That's an. And I of x, so at what speed? And I of x tells you exactly at what rate the probability goes away from the point x. In what sense? In this sense. Okay, this I completely don't want to enter this framework because also it's not particularly interesting, but you can think that you can consider, like, you have your space E, and you can consider the space of compact subsets of E. And there are a lot of functions that take a compact set and give you a number. For instance, a probability. You can think that the probability is something that takes a compact set and gives a number. If you know, in these nice topological spaces, if you know probability measure on compact sets, you know it's everywhere. So it's enough to know it on compact sets. Or also I can take a number A, a probability measure mu, and associate a compact A, for instance, minus log of mu of k divided by this number A. Or for instance, I can take a lower continuous function I and consider the map that associated to a compact set K, the infimum of the compact set. These are all lower continuous functions from the space of compact sets to 0 infinity. Now, okay, I don't want to enter this discussion, but this space of these functions can be itself equipped with a compact topology, compact. So whenever you have a sequence, you can extract a converted subsequence. This means that if I take so okay, and now in our this statement I up bar equal to I down bar is exactly the statement that in this space measures, so functions of this type, minus log of mu divided by k, converge to function of this type. So since the space is compact, if you give me a sequence Mn, I can always find a subsequence for which along this subsequence I up bar and I down bar will be this, oops, they are here. So I up bar and I down bar are the same. This may be trivial. This, I mean, if I fix x, this is trivial because I can take, it's trivial, probably it's trivial because I can take, for each x, I can take a subsequence for which this converges, okay? Like in which the lin sup is equal to the lin min. But the statement is that the subsequence is the same for all the x. Okay. Good. So yeah, so along a subsequence, this this kind of equality exponential equivalence will always be true. Notice, however, that okay, now you give me, I don't know. Okay, let's for instance, yeah, let's go ahead a little bit. For instance, suppose that you are on 0, 1, and you give me a sequence of probability measure, which is just, it has some density, e to the minus n v of x up to some normalization constant with respect to Lebesgue. In this case, it's very easy to check that an should be n, and I of x will be v of x, this exponent here, minus the infimum of v. Because if you check what is mu n of a set, of an interval, say, for instance, okay, you have to integrate over this integral. It's the integral v to the minus n v of zn over this interval. And then you have to take 1 over n log of this. So of course, what will matter is the minimum of v over this interval. So in the neighborhood of point x, this will be roughly v of x, and Zn will give you the infimum of v. Of course, v is defined up to a constant. When I write this, so this constant is such that the minimum is 0. I don't know, it's quite intuitive that the measure e to the minus n v of x dx, if I have to give you the speed and the rate, the speed should be n and the rate should be v of x, right? So, good. Okay, but then you can tell me what happens if I chose an, in that example, I chose an equal to n square. You will, okay, this will still be true. Just I of x will be 0 everywhere in that example. If I take an, so if I take an equal to n, I of x will be v of x. But if I take an equal to n squared, for instance, I of x will be 0, because this tells you that this probability measure concentrates. So before it tells me concentrates with speed n. So like the probability of being close to a point is e to the minus n I of that point. So, but this, if I want to write it as e to the minus n square on this rate square in this logarithm, in the sense of these limits of logarithms, will it concentrates as e to the minus n square times 0, which is a way of saying that it's small, but not as small as e to the minus n square something. It's as small as e to the minus n something. So, I don't know if it's clear. I'm saying what I'm saying. I'm saying that if you give me any sequence of probability measure in a nice topological space, and any sequence an that goes to infinity, I can find I of x for which Mn, for which the probability measure has this form when n goes to infinity. In what sense? In the sense of these inequalities with closures and interior offsets. Okay, I can find this I of x, at least on subsequences. Okay, but this, what does it tell me? So in some sense, if you choose the wrong an, you will get that I of x is either 0 or infinity. So it will be non-trivial only if you choose an, the right concentration speed of Mn. Okay. So it could be that there is more than one relevant scale that, I don't know, for some, on some part of the space, some an is relevant, on some other part, some other an is relevant. So I of x will be plus infinity somewhere and finite somewhere else, and vice versa, 0 somewhere, non-zero somewhere else. But still, if you only get two values, 0 and infinity, this means that you took the non-interesting an. You can prove that there is always an interesting one in an for which there is a non-trivial I, which is not 0 or infinity. So it's like to say it's general properties of sequence of probability measures. Sequence of probability measures either converge or either converge to something with a global support, or they concentrate. There is no other option. So you can check then from this kind of statement, you usually can recover convergence, because you see Mn of an open set behaves as e to the minus an, the infimum of the open set of I of x. So this tells us that, so for this not to go to 0 exponentially, but to stay close to go to some positive numbers, this means that I of x, this means that the infimum of I of x of A is 0. Yes, it's 0. Otherwise, you get something that goes to 0. So if this stays positive, it means that there is a point in x where I of x is 0, which implies that any limit point of Mn must be concentrated on the zeros of I. Okay, this example we checked. So what, another example, what we proved before, if you want, is exactly this principle, okay? For what? For Mn. So we took E, the probability measure on G, in this example of IID random variables, E, the probability measure on C. Mn, the law of the empirical measure, and An equal to n, the speed equal to n, and Mn to be the law of this empirical measure. And we found that this functional I, this rate is called I, function I from e to 0 infinity. So it's a function that takes a probability measure and gives me a positive possible infinity number, is the empirical measure of mu with respect to n. Read the classical result. Okay. Again, we proved okay, we will check this second more probably. But in some sense, we exactly computed this I of x up, I of x down, where the space E was the space of probability measure on G. So this x is a probability measure, and I of x, these two are the same and are equal to the relative entropy itself of the probability measure with respect to the reference. Yes, so one could do, we will do it a bit, same kind of statements, maybe for empirical measures or other objects, for Markov processes or dynamical systems. Okay, so let's go back to the proposition that I say we will try to maybe prove. So again, we are on a general topological space. We have a sequence that goes to infinity, an, and the sequence of probability measures, mn. We have no other assumptions. And we define these two objects. So I of x, we define I up and I down of x, depending on the inf and lim sub, I of x, as the limit, the infimum over all the possible ways that I converge with the probability to x of the relative entropy of mu n with respect to mn, to respect to my sequence, divided by an. Good. And we want to prove that, okay, that was, we want to prove the proposition, this proposition, that I bar, so the one with the lim sub, for instance, is the largest lower semi-continuous function. Did I exchange the two bars? Yes, so this is down bar. I think so. It's very tricky. Sorry. This is here. The bar is down. The two bars are exchanged. Sorry. I think so. Because there are a lot of minuses. And, but yes, the smaller one. Yes. So it's the largest semi-continuous function, I. So consider all the lower semi-continuous functions that have this property. The smallest, the largest one is exactly I bar, this one with the empirical measure and so on. And okay, if you want the opposite inequality, but on open sets, then the best function you can check even out of the set of lower semi-continuous is I up bar. The best, so you see that here the inequality is less or equal, so the best function is the smallest. Here is bigger or equal, so the best function you can put is the largest. Okay? So let's prove this proposition. So this tells us that there is a one-to-one relation in the optimal way of cheating, of converging to x and not to whatever mn did, not to possible limits of mn, but to point x. And what is the probability that mn is close to that point? Okay, it's quite intuitive in reality, and indeed the proof is not complicated. However, so let's prove 14 on, no, let's prove 12. What is 14? Maybe I gave two equal labels, sorry. This is 12. So let's take an open set, and let's take a point in this open set. Okay, we want to prove that the 1 minus 1 over an log of mn of O in the limit is bigger or equal than I bar of x first. So we have to prove, we have to prove that this I bar up and down satisfy the two inequalities in the proposition and that they are the optimal ones. We have to prove these two statements. So let's do it, for instance, for I up bar. Okay, good. So we have to prove first that we have to prove that for any set A, it satisfies this. and we have to prove that it's the best one, I have bar. So out of all that satisfies we, or the other I are smaller than it is, are larger than it is. Good. First, okay, I can of course take A to be open, because if I take the interior, the inequality goes in the good sense for me. So I can take A to be an open set, because on the right hand side there is only the interior. So so let's fix an open set. Let's fix a point in this open set. And let's take a sequence µn that converges to the delta of this point. And then, okay, so this I bar of x was the infimum of all these sequences, but it's immediate to check that this infimum is realized. So I can take a sequence that satisfies it, okay? So there exists a sequence µn that goes to delta over x, such that the lean soup of the relative entropy divided by an goes exactly to I bar of x, the optimal one. Good. Then I just make some very trivial inequalities. The logarithm of the probability Mn of this open set, Mn is, okay. This I write, okay, first, if you want, I just write it. This is by itself is equal to this. Is equal to dmn in dμn over O, the integral over O of this object. Okay. With no loss of generality, you can assume that Mn is absolutely continuous to μn. You can always add epsilon Mn to μn. So this makes sense. And then I just, okay, then there is a log, and I just divided by 1 over μn of O and added the log of μn of O. So here I removed and here I added the same. Okay? So this first inequality is true. Mn of O is the integral over O of 1 in the Mn, so I can write it as dmn in the μn. Now, log is a concave function. So the log of the average, so you see that this is 1 over μn. The μn is an average, what is inside of the log here. So it's bigger than the average, since it's convex, it's bigger than the average of the log. So it's bigger than 1 over μn of O, the integral over O of the log of the same stuff. Okay, plus log of μn of O. Oh, now this log of μn in the μn is minus the log of μn in the mn. So if instead of integrating just on O, I would integrate on the wall space, I would have exactly minus the empirical measure, this integral, minus the, minus the relative entropy. Sorry. This integral, if instead of just O, there would be everything, I would get minus the empirical, the relative entropy. So I write minus the relative entropy, that is still divided by 1 over μn of O, plus, okay, the remaining, the integral of the complementary of O, yeah, O complementary here, I mean with this bar, not the closure, the complementary, plus, so the same functions on the complementary, but yes, because here there was a minus. But this is not a big deal, so this would be the μn, and now I write it, this dμn, I rewrite it again as dμn, dmn. So that's all this stuff. Why I did this? Because look, now this the function here that I integrate in dmn, which is just what remained from this integral when I removed the whole relative entropy. This is something u log u in dmn of some set, but u log u as a function is bounded by 1 over e, by minus 1 over e. Is always bigger than minus 1 over e. So all this stuff is always bigger than 1 over μn of O, okay. This parenthesis is extra, it's not there. 1 over μn of O minus the relative entropy minus 1 over e. Because this integral, I don't know to compute it, depends on μn and so on, but certainly doesn't exceed e to the minus 1. Plus this log of mn. Okay. Now, however, μn was convergent to the delta over x, and x is a point inside an open set. So since this convergence means convergence for all functions, of the average of all functions. So if you take a function which is like 1 inside O, and then in particular over the point x, and then goes to 0 within this neighborhood O of x. So we are using that this topological space is good enough that we can separate points with functions. It's not important. Mu n of O, this is actually, yes, this is true in a lot of cases. Mu n of O will have to go to 1. Okay? If mu n converges to the delta over x, and x is a point inside an open set, the measure of the open set needs to go to 1. Since, okay. So we have that now, okay, we have this inequality. We take minus, reverse the inequality, divide by an, take the limb soup. Okay, tac, tac. So when I take the limb soup, divide by an here, what happens? Well, 1 over an with the minus, log of mu n of O goes to 1, so the log goes to 0. I divide by an, that goes to infinity. Certainly this guy goes to 0 in this. But also e to the minus 1 divided by mu n O, they go to 1, and divide by an goes to 0. And what remains is 1 over an. I change the sign, h of mu n given mn. Okay, again, divide by an. I should also divide by 1 by mu n of O, but this is going to 1. So in the limits, I can remove it. And now this is, so this is exactly, this limit is exactly I bar of x. So you see that, that the formula that we wanted to prove, formula 12, holds for with I equal to I up bar. Okay. We proved that for every open set, and for any set, if I here I put the interior, this holds with I bar. Okay. Now I have to prove that it is the optimal one. So I prove the opposite. Suppose that formula, sorry, this is always 12, the formula with the, in the proposition holds for some I of x. Okay, I can assume, I will assume that this I of x is lower semi-continuous. This in the statement there was not, because if it's true with some I, it's true with lower semi-continuous envelope. Okay, it's a small detail. So I can for free assume that it's lower semi-continuous. And then I define mu n delta, mu n epsilon, not delta, because there were already too many deltas, so I decided to call it epsilon. So this is epsilon. Mu n epsilon. The measure Mn, original reference measure Mn, conditioned to be in a ball of size epsilon around x. Okay. Okay. If x is not in the support of Mn, so if this ball is measured 0, take mu n delta, mu n epsilon to be all concentrated already in x. It's irrelevant in this case. Okay. Let's compute the relative entropy. Okay. So what is the relative entropy of mu n epsilon with respect to Mn? So the density is 0 everywhere, but on this small ball. And on this small ball is the density 1 over Mn of the ball. So the relative entropy, you just compute it explicitly because it's the integral in the mu of the log of the density. This integral in the mu is just an integral over the ball. And the ball has measure 1, and over the ball, for mu, and over the ball, the density is 1 over Mn of B epsilon. So this integral is minus the log of Mn of the ball. Therefore, if I take the limit when n goes to infinity of an, a mu n, the relative entropy of mu n epsilon with respect to Mn, I get the limit of 1 over n minus the log of Mn of B epsilon of x. I was assuming that Mn satisfied this inequality with some I of x. I was assuming this inequality for some I of x, okay? I'm assuming this inequality for some I of x. Then you see that I found a sequence of probability measure, mu n epsilon, okay, they still depend also on epsilon, for which I have this bound, because it's exactly the same bound that was in Formula 12 in the proposition. That's exactly what I was assuming when the set A is a small ball of radius epsilon around X. Now I take a subsequent, okay. So you see, if I take n, so if I take n to infinity and then epsilon to 0, since I is lower semi-continuous, the limit when epsilon comes to 0 of the infimum over ball of I of y goes to I of x. That's exactly the lower semi-continuity property. If I take the infimum of a small ball and then I shrink the ball to one point, the infimum will converge to the value of the function in that point. By lower, this is true for all lower semi-continuous functions. At the same time, at the same time, mu n is concentrated on a small ball of radius epsilon around X. So when I take epsilon to 0, say joint, no matter how I take epsilon with 0 with n, this will converge to the delta over X. And now it's just a diagonal argument to tell you that you can send epsilon n to 0 slarely enough so that you have both, you will have at the same time that mu n, that is mu in n epsilon n, converges to the delta x, and the inequality on the relative entropy. Okay, so we proved that if you have I of x that satisfies this inequality, then you have a sequence for which that pays an information at most I of x. So I of x is bigger than the optimal cost of the information. So this means I found a sequence mu n for which that converges to the delta over x, just using a diagonal argument. For any n and epsilon, I have this inequality and this convergence. Therefore, there exists a subsequence epsilon n that goes to 0 slowly enough, for which I can do it in just one sequence. Okay, it's a completely general, it's called a diagonal argument, right? So, so cool. What I'm saying then is that if an I satisfies this inequality, this I find a sequence here for which this limit is I of x. So the sequence may or may not be the optimal one, the one doing the infimum here. So I bar is certainly smaller than this I of x. So that's the optimal. Okay. So again, this I up bar is the smallest function for which this inequality is true for every set, measurable set A. And okay, let me skip the proof that I down bar is the optimal one for the reverse inequality. The proof is not just the same, it's a bit different, but not much. You play a bit with small balls and logarithms. Okay. So let's skip the proof of 11 that okay, the lim-inf is the optimal for the reverse inequality. It's not completely, I mean, it's easy to prove, but it's not completely intuitive because one is just, they are lim-sup and lim-inf of the same thing, but one is the optimal for the inequality and one is the optimal for the reverse inequality. One is the optimal on open sets, one is the optimal on open sets, on closed sets, one is the optimal on closed sets. So, but the proof is again, it's more or less similar. Okay. And the other bound I wrote follows more or less similarly. It's the same level of, say, the figure. I don't know, there are questions on this proof. So again, we are saying that calculating the probability of sets with small probability is equivalent of calculating the optimal way to cheat, okay? Just sometimes it's easy to compute, to give bounds on probability of sets. Sometimes it is easy to give strategies to cheat, to create another measure that converges. And indeed, yes, and indeed that's exactly what I want to tell you. So what we obtained, we consider a reference sequence of probability measure on our space E. And then we consider sort of a fluctuation speed, an that goes to infinity. We want to see how small is the probability of Mn of a set when small is defined as e to the minus an some constant, okay, some number, this small. So what we want to prove is, if you want, you can write it on set, but it's equivalent to write it on small balls, that the probability Mn, when you send n to infinity and then epsilon to 0, in the sense of the logs that we've seen before, that Mn of a small ball around the point x goes like e to the minus an I of x. If we want to prove something like this, that again, at least along some sequences will always happen, what do we have to prove? Well, we want to find I. This will all happen by instance, but the interesting thing is who is an and who is I, who is this function I. So we need to prove two things. We need to prove, if we want to prove something like this, okay, to know how the probability of every small chunk of space goes, we need to prove two things. We need to prove that, I don't know, that there is oh, here I should divide by an, of course. Here is divided by an. This relative entropy. Of course, I need to find a sequence. I need to prove two things: that no matter how I converge to x, or to the delta over x with a measure, I have to pay an information price at least I of x. First bound. Second bound, there is a way to converge to x that pays at most I of x. If I prove these two, this tells me, one tells me that I of x is bigger than I down bar. This tells me that I is smaller than I up bar. So since I up bar is also bigger than I bar, it means that all these are equal. And so this I is equal to I down bar is equal to I up bar is equal to the rate of my measure. So I need to prove these two sequences, these two statements. Is it clear? If I prove A1 and B1, I've proved in the sense, logarithmic sense, in the sense of information, all these equivalent things, this kind of statement. Okay, just I want to remark, because this is often comfortable in proofs, is that I can replace A1 with the following statement A2, exactly because this is equivalent to exactly thanks to this proposition. There exists a family, I alpha, from e to 0 infinity, of lower semi-continuous functions, such that their supremum point-wise is equal to I of x. Supremum of lower semi-continuous is lower semi-continuous. So this I of x is certainly semi-continuous. So, okay, the I of x in A1 and B1 should be the same. That's otherwise, okay, it's called I of x indeed. So, such that the supremum is exactly I of x, and for each compact set and each alpha, I have this inequality, 17. This inequality 17 is exactly this, but written for A compact set. Because if I want it for some A, it's the same to have it for a closed A, because due to obvious inequality, it's enough to have A closed. We are on a compact space, so closed is compact. So again, so that's for formula 11. You see, suppose that I have this 17 for each alpha, Then this tells me that I alpha is, for each alpha, I alpha is not bigger than I down bar. This means 17, thanks to our proposition, 17 means that I alpha is not bigger than I bar, down bar. Down bar I. Yes, no, not bigger, not smaller. There is always a lot of minuses in here. Just a second, sorry. Yes, is the yes, because it's the largest. Okay. Sorry. Yes, this tells me that I alpha is not is smaller than I bar. So since I know it for every alpha, I bar is also bigger than the supremum of the I alpha. Okay? So if I prove this inequality for each alpha, I prove it with the supremum. Okay? This statement is non-trivial. It's due to the existence of this optimality. It's due to this, I don't know how to say, usage of information and so on. Because it's not, if I just take the supremum over alpha inside the formula 17, what I get is supremum over alpha of the infimum over x. I'm saying that you can take infimum over x of the supremum over alpha, which given that the inequalities in this side is in general is not true. Indeed, I'm not saying that for every compact set, you can do it. I'm saying that if you know it for every compact set and for every alpha with I alpha lower semi-continuous, you can exchange the infimum and the supremum. Why? Because once you know that the alpha is less than the optimal one is also bigger than the supremum on the alpha. That's all. So very often it's simpler. So when we want to prove this kind of statement about course of information of probability of sets, or even just convergence, for this bound, for the second one, it's really very powerful tool to compute this relative entropy. Because you see, I need to find the sequence mu(n). For each x, I need to find the sequence mu(n) that converges to delta x. So you give me delta x, and I can sort of imagine a mu(n). It's my task to find the sequence mu(n) that concentrates on x. And for the way a lot of processes or a lot of probability measures are built, it's easy to compute explicitly relative entropies. So one has a chance to prove something like this, like if you take reasonable classes of mu(n), because mu(n) is up to you to build it. This A1 is a bit less comfortable sometimes in practical problems because you don't know anything of mu(n), it's just a sequence converging. So this technique is rather useful to kind of change, to prove this kind of statement A2 is equivalent. From what we have seen, this is equivalent. No, it's equivalent. It implies, it's enough to prove A1 or B1 to prove these weak large deviations. What we also checked is equivalent also to prove, it's enough to prove A2 and B1 to prove large deviations. Because from A2, I get that down bar I is bigger than I. A2 implies that down bar I is bigger than the super of alpha, so I. Down bar I is bigger than I. B1 implies that A bar I is smaller than I, and since they are also, I down bar is also smaller than I bar, all these are the same, so I found I of x. So I think we will very rarely, we will probably never use in these lectures A1, even if kind of theoretical is a nice way, like no matter how you converge, you pay at least the price I of x. That's what you should prove. We will rather use this formulation A2. Okay? We prove these bounds for a family I alpha, and then we prove it with its supremum, which a priori is non-trivial because you don't have for free the right to exchange sup and inf. Okay. Yeah, okay, last remark. So this is still, we went to finitely many sets, a bit of maybe general framework, but last remark, and then we go back to a more concrete example, but less trivial than before. So I of x, what it does, it describes the fluctuation properties of my sequence Mn. Mn of typically goes to a point, for instance, but the probability of being close to x and not to the point where it goes is to e to the minus in I of x. That's the idea. So if we have some random object, like for instance, I don't know, our Markov process, we can consider observable some functions of this process, for instance, the empirical measure. Okay? But observable, sometimes they can carry more information, they can carry less information. For instance, the empirical measure was carrying the information of the sequence up to reordering. Good. But I don't know, I could make richer observable, richer functions of the sequence, or others that take, I don't know, even less information. So if I know the intuition is that if I know how some observable, which takes a lot of information, fluctuates, I should be able to derive from this the fluctuation of an observable that carries less information. Okay, this is true, and it's trivially true. So it's just a property of push forward. If I have a sequence µn that satisfies the large deviations, these all equivalent inequalities with rate I, so if the fluctuation of Mn are described by this function I, and if I have a function from my space E to another space F, which is also should be nice, and this function is continuous, then the push forward domain of Mn through F satisfies large deviations on F with the rate with this J, which is the infimum of I over the fiber of F. I don't know if it's like, suppose that Mn is the law of a random variable xn. Mn is the law of the random variable xn. Then I consider random variable y, which is f of x, okay? If I knew how xn behaved when n is very big, if fluctuations of xn were described when n diverges, I will know how the fluctuation of f of xn will be described when n is very large. Okay? If f is invertible, there is as much information in x as in y, but if n is not invertible, f of x carries less information than x. So I need this infimum is an infimum, just 1 point in general. So Mn is the law, you can think that if Mn is the law of a random variable xn, Mn composed with f minus 1, the push forward of Mn through f is the law of f of x, right? So okay. This remark is trivial and we can prove it using our characterization of I of x as the optimal limit cost of the relative entropy. I again forgot to divide by an here. So divided by an. So okay, it's let's take for instance the one with the I up bar, okay? Because actually, even if large deviation do not hold the same bounds, you could do a J up bar and a J down bar, of course. So, for instance, so fix a point in the second space, and we need to find a sequence of probability measures such that the relative entropy divided by n converges to J of y, this guy. Okay, so we consider f minus 1 of y. This is compact in E, because 1 point is closed, the counter image is closed. Because f is continuous, this is very important, f is continuous. So there exists a point in f minus 1 of y, which minimizes I, there is a point which, such that I of x is equal to the infimum over f minus 1 of y of I. This fiber means f minus 1 of y. So this guy is an x. So since I'm assuming that Mn satisfied large deviation on E, there is a sequence that converges to a delta on this minimizing point x, such that the relative entropy divided by n converges to is not bigger than I of x. It converges to I of x. So since f is continuous, the push forward of this µn converges to the delta over f of x, which is delta over y. So you see, I found the sequence of probability measure on f that I fix y. I find the sequence of probability measure on f that converges to the delta over y, and such that the lim sup of the relative entropy, the relative entropy of push forward is no bigger than the relative entropy of the original measures, because by definition of the relative entropy. And so this is no bigger than I of x, because µn was optimal for I, which is exactly J of y, because I of x was the one realizing this. And the other boundary reason similar. So, okay, so that's just, you know how random variable xn fluctuates. Through this formula, you know how random variable f of x fluctuates. That's all. So the richer is the observable for which you can establish fluctuations, the stronger is the result, provided you can solve or say something on this variational problem. Okay, let's go back. Oh, in the last 5 minutes or 7 minutes to our Markov problems. We have a finite graph, finite G, transition probability Pxy on G, and okay, and I want to give to G a structure of graph, which is very natural. I take the set of edges of G directed. Okay, so there are points, and I want to put arrows from one point to the other. So I put an arrow from X to Y if the probability of going to X to Y is strictly positive. I don't put arrows when there is zero probability of going to X to Y. And I assume that this graph is connected, so I can go from each point to each point following arrows. We discussed this hypothesis last time. And now I take two objects. If you give me, still no probability if you want now. If you give me a path, a function from n to g, times 0 here, times 1 here, and so on. I want it, of course, such that each xi plus 1 for every I is in S. Okay, this path follows arrows. I take a path which is compatible with my Markov structure. And I built up two objects. The first is the empirical measure. Okay, I put a small rock on each point I visit of size 1 over n up to time n or n minus 1 if I start from 0. And then I want to consider a current, an empirical current, which looks a bit the same, because on the graph this is not seen very well. But this is just 1 over n, again, the sum of deltas over the arrows I visit. Okay, so I have this graph. This guy tells me how much time I spent on what points, how many times I passed on each point. And this guy, this is a measure on the spaces of edges and tells me how many edges I crossed up to time n. Okay, so I put a small weight, 1 over n, over the arrow x to y. When I'm x, I go exactly to y. Now on the graph, this is a bit misleading because this is still a probability just on the spaces of edges. But if you do it on geometrical objects, so not a graph, but for instance, a manifold, this will be a random, what's called a current indeed. Yes, dual of one forms. So it will be like, okay. So this is a sort of a tangent object. And this is an object on the space. And this is a sort of a tangent object. But for us, these are two probability measures, one on the vertices of the graph and one on the edges of the graph. So now if x, so this, you give me a path of length n if you want, I give you these two probabilities. Now, if the path, I take it random, build using the Markov process that we built last time. So I start in a point, then I jump to point y. If I'm in x, I go to y with probability pxy at each step. This pi n and this qn will be random again. Okay, so the law of the couple pi n qn, what it is a probability measure over what space? Probability measure on G times probability measures on S, the space of the edges. Sorry, I had called the space of the edges E, then I realized that we called E something else already before. So I called S the space of the edges. So this is the law of pi n qn, the law of a couple is the probability measure on P of G times P of B, P of S. Okay? Two probability measures, this and this. They are both random, and the law of the couple is a probability measure on the product space. Okay, so our next, so we reviewed a bit what does it mean to find this rate. You give me a space and any sequence of probability measure, there is this functional I of x, which is somehow interesting. It tells me how these random objects fluctuates. It tells me what's the cost of cheating, what's the cost of making them converge somewhere rather than they would naturally go. Yes, like the empirical measure here will naturally go to the invariant measure. What's the cost in terms of information of making it converge to something else? What's the cost of cheating? Which is the same thing as saying how fine descriptions of the fluctuations of pi n. Okay, You can, maybe we have seen a bit of motivations last time. So I don't want to write you a theorem now. I of x is the I of measures, and we should find a function on this space, P of g times P of a to values with 0 infinity. I don't want to write this function. I want to find it with you. So first, so there is a case when we checked it already, yes? If we take not a Markov process, but an IID sequence, and we don't look at Qn, we look at a simpler observable, just pi n, that carries less information. So, but you know, if I know something that carries less information, the rate will be the same. So at least in the IID case, I know that the speed should be n, an should be n. So here also, there are cases, okay, even in this context where non-trivial speed other than n exists, but an, we take it equal, so the relevant one is an equal to n. If we get an bigger than n, we will get always like n square, our I will always be 0. We will get it less than n, it will always be plus infinity unless on the invariant measure. So the example we made at the very beginning with the independent random variable strongly suggests us to take in equal to n, which it doesn't cover. Okay, no, not important to make a color. In equal to n. Because we have got this. So we only need to find I, the rate. This is a function that takes a probability measure on the vertices, takes a probability measure on the edges of the graph, and gives me a number in 0 infinity, okay, infinity included. Okay. And this describes like how improbable is not to converge to the typical measure and the current, but to one that I decide. I weight n, how unlikely it is that after n steps, I'm not close to the invariant measure, to the stationary current, but to something that I choose, mu and there. So here mu is a probability measure on G, R is a probability measure on the edges. Okay, let's introduce a very simple formalism. So, okay, first thing is, what can we produce in the limit? There are like, probably there are some mu and there that are like impossible. Even if I can cheat, I can make this Markov process, this path, take it with a completely different probabilities and so on, but there are probably some mu and there that I will never find a sequence to which it converges. Let's check. So if I take a function from G to R, from the vertices to R, so on each vertex a number, the differential of this function will be a function on the edges to R, which is just df of xy is f of y minus f of x. Okay? If you make a graph and you make it scale to its like if it has an asymptotic cone, for instance, you make it scale to say a manifold, this thing will scale to the differential on the manifold. So if R now is a measure, not necessarily probability. Why did I put this? Okay, if is a measure on S, not necessarily probability, this star R, the adjoint of the differential, will be a measure on the set of on the graph, on the vertices of the graph, which is just the dual of D. So D star R, what measure on the graph is the measure that when I integrate a function on the vertices, is R the measure on the edges, the integral of df with respect to R. It makes sense, yes? So if I have a function on graph, df is a function on edges. If I have a measure on edges, d star R is a measure on the vertex, okay? You see, d star R, I have to give you a measure on the vertices. I define it through integration. Is the measure that when I integrate the function f is R, the integral over the edges in dr of the differential of f. For instance, okay, if I take Qn, you give me a path x, I take who is this star Qn when I integrate a function f. Is 1 over f, the sum I have to integrate with respect to the Dirac delta f of y, this df of x and y, over the delta xi minus 1 xi. So it's f of xi minus f of xi minus 1. So this star qn of f is just is a telescopic sum, is f of xn minus f of x1 divided by n. So you see that it's not important how you make fluctuate xn and x1. F, is bounded, we have a finite space. It's quite intuitive that any possible, no matter how you choose your probabilities, any possible limit point of the law of Qn will concentrate on some current R, which is closed, which has this thing equal to 0. Yes, this star R must be equal to 0 for any kind of reachable R, because it's true that here there is some, with n it's something small, but it's not something small that with some probability can be big. Okay, we will prove it more, but just we are trying to guess, yes? We are still in this stage where we want to find out I of mu and R. So the first thing is that R measures on the edges that do not have, that are not in the kernel of the star must be unreachable, must have a probability which is not exponentially small. It's really 0, okay? So I will be plus infinity there, which if you check the inequalities means that this probability of being in the neighborhood of something which has non-zero, this star is okay, goes to 0 faster than an exponential, and here is actually 0 from n for n large enough. Also, if we define a map from edges to vertices that takes an edge and gives me the first vertex, then just by this definition, when I apply it to Qn, I get exactly pi n, because okay, Qn is the sum from 1 to n delta xi minus 1. If I apply E, or if I do the push forward of Qn via E, okay, it means that I forget the second variable, and okay, the sum from 1 to n xi minus 1 is 0 to n minus 1 xi. So again, since this is a closed space in our space, it's a closed subset of our space, you can invent the probability measure you want. You will always live on this subspace. Okay, it's not like you can make Qn fluctuate away from where it is with probability 1. Outside, the probability is 0. So again, I of mu and R will plus infinity unless so you can change what Qn does, you can change what Pn does, but this relation between the two will pass to the limit. So any limit, because it's continuous, so any limit point will still satisfy this equality. This means that I must be mu plus infinity if the equality is not satisfied. And unfortunately, we have to, I wanted to give you a small exercise, but we are out of time. Okay, sorry, we started maybe 5 minutes later, I finished 5 minutes later, sorry. I didn't realize the time was over. If you have questions, I'm happy to answer them also by email or something. Thank you. Well, now, if you want, but I understand that I'm late already. So for you, I'm not late myself, but if you have a question, I can answer now, but if it's late for you, I can answer by email. Okay. So
if there are no questions, should we finish?
Yes, it's okay.
Спасибо, до свидания.
До свидания.
Да, встречаемся через неделю. До свидания.
Через неделю.
Спасибо, до свидания.